Okay, now that we discussed sandwich stoichiometry and how to predict how many sandwiches we could make with certain ingredients, and then how many ingredients we would need to make certain sandwiches, let's now apply the same concept, the same logic to balanced chemical equations. Predicting amounts of substances in a balanced chemical equation from another amounts, that is what stoichiometry is all about. So before we start these problems, let's go ahead and review the 5 steps of solving any stoichiometry problem. Number 1, look at the balanced equation and make sure you balance it if it's not done if it's not done already. Number 2, inspect the mole ratios in the balanced equation. These are those coefficients listed before each substance. Next, write down what the problem is asking for on the right hand side of the page and write down the information you know, what's given to you on the left side of the page. Let's make sure for both of these that we have units and we're writing the substance we're talking about. Lastly, let's use conversion factors to cancel out units until we arrive at what you're looking for. So let's look at problem 6a here on page 21. So the question is revolving around this reaction above. N2 plus 3H2 yields or produces 2NH3. Now since there are numbers here already, we're not trying to trick you, so that's already balanced for us. If there are not coefficients or values here, that's when we need to make sure to balance it. So now 6a, how many H2 molecules? This looks like a question to me, so I'm going to write down molecules, H2 on the right hand side of the page, will be needed to react with 6 molecules of N2. So this is what's given. I'm going to go ahead and write that on the left side of the page. Now this is kind of like saying how many slices of cheese do we need to react with 4 slices of bread. Instead of cheese and bread, though, we're talking about chemicals in this balanced equation. Now when we're going from molecules to molecules or moles to moles, looking on the cheat sheet, this is always going to be one step. And the only thing we need to look at are the balanced equation ratios. So that's what we're going to use. Now looking at the balanced equation, it looks like for every 1 molecule of N2, we need 3 molecules of H2. I'm going to put that 1 molecule N2 on the bottom so that they cancel. And I'm getting the number 1 from the balanced equation. Essentially, there's a 1 there because there is no number. And then for that 1 molecule of N2, it reacts with 3 molecules of H2. And I'm getting the 3 again from the balanced equation. Now the molecules of N2 will cancel, and 6 times 3 is 18. I'm actually going to go back and I'm going to make all of these 2 sig figs at least so our answers work out better. So 6.0 molecules, and we're going to get 18 molecules of H2 reacting with that. Okay, let's check out B. Very similar process here. If 3.0 moles of N2 reacts, it looks like that's our given. 3.0 moles N2. I'm going to go ahead and add those point zeros just to make the sig figs work out better. With exactly the right amount of H2. So this means that the amount of H2 is the perfect amount to react with this, so we kind of don't need that information then. How many moles of NH3? There's our question. Moles NH3 will be produced. So again, we're going from moles of one substance to moles of another substance. Moles to moles problems are just one step, and all we need to do are use the balanced equation ratios. I'm going to look back up at my balanced equation. It looks like for every 1 mole of N2, it produces 2 moles of NH3. And then 3 times 2 divided by 1, 6 moles of NH3. Okay, problem C. If 3 moles of NH3 is produced, that's our given information. It doesn't matter that this is a product. Again, I'm going to make that 3.0. How many moles of H2 must have reacted? So that's what we're looking for. Moles to moles, one step. The only thing we need to use is the balanced equation ratio. Now it looks like for every 2 moles of NH3 produced, we will need 3 moles of H2. So I'm going to put 2 moles NH3 on bottom, 3 moles H2 on top. Okay, 3 times moles of NH3 cancels. Oops, I forgot to cancel that out up there. So 3 times 3 divided by 2, and we get 4.5 moles of H2. Now, although we can't have half a molecule, we can have half of a mole. So we can get decimals for any answer involving moles or grams. Okay, let's move on to a new equation. So the first thing we should do again, always, is make sure this is balanced. There are coefficients here already, so I'm going to go ahead and give that a check mark. It looks like this one's already balanced again. Now 7a, how many moles of F2? That looks like the question. I'm going to write mole F2 on the right are needed to react with 1 mole of NH3. So 1.0 mole of NH3. How many moles of F2 are needed to react with that? It's a moles to moles problem, so again, just one step. Let's look for those balanced equation ratios. It looks like for every 2 moles of NH3, we need 5 moles of F2. So 1 times 5 divided by 2, and we get 2.5 moles of F2. For 7b, if 6 moles of NH3 reacts, looks like that's my given, with the correct amount of F2. Again, this just means that the amount of F2 isn't really relevant to this problem. How many moles of HF will be formed? So I'm going from moles to moles. That's one step. The only thing we need to use are the balanced equation ratios. It looks like for every 2 moles of NH3, again, I'm getting that number from the balanced equation, we can produce 6 moles of HF. And 6 times 6 divided by 2, 18 moles of HF. Okay, last one. If a reaction forms 9 moles of HF, again, that's our given information. How many moles of F2 must have reacted? There's our question. Okay, we're going from moles to moles. Again, it's one step. Let's look at our balanced equation. It looks like for every 6 moles of HF produced, let's put that on bottom so it'll cancel, we will have needed 5 moles of F2. And 9 times 5 divided by 6, we get 7.5 moles of F2 as our answer. So again, for moles to moles problem, make sure you are doing one conversion, and the conversion factor is going to involve the balanced equation ratios, which are the numbers before all the substances in a balanced equation.